All right, so here's exam 1 for 125, and let's go through each of these questions. So a solution of sugar in water is an example of, since sugar will dissolve in water, that would be homogeneous mixture. Which of the following represents diatomic element? So diatomic means two of the same elements that form a molecule. So O2 is diatomic. O3 is not, it's triatomic. So the other ones are all different elements. Number 3, what is the result of the correct sig figs of the following calculation? So what you would do is you would divide 21 divided by 5.8 first. You'd get a number, since obviously you get a number, but since the product and quotient needs to be in the least number of sig figs of the number, you'd have 2 sig figs there. Then you would go through and add the first 2 numbers, which then it would be the least number of decimal places, and then subtract, which would be the least number of decimal places. So if I were to do this in my calculator, let's see, we have 21.58, or no, 21 divided by 5.8, and that would be 3.62 or 3.6. If I take 881 plus 3.6, that equals 884.6. But since I only need to have it to 1 digit place, it would then be 884, since we would round up. Then 884 minus 2.14 would then be 882.46, or just 882, because we need to have it to the ones place, because the ones place would therefore be the least precise decimal place, or least sensitive position. So it'd be A. All right, so pressure of a gas cylinder is 14.7 pounds per square inch. What is the pressure when expressed in kilograms per meter squared? So these ones we're not going to cover in incredible depth, but basically what I do and what we learned in the beginning of the semester is we're going to go through the conversion in steps. So the first easy thing to do is take the 14.7 pounds and convert to kilograms. After you're done with that, you're going to take the inches squared and you convert that to meters squared. And the way you do that, you can square all of these distance units. So you'd have 2.54 squared equals 1 inch squared. So it would be around like 12 point something. And then, 5 point something. And then you can convert that centimeter squared to meter squared, and then you can do that conversion from there. And then you'd end up dividing the kilograms by meter squared. So the next one, manganese to the density of 7.3 grams per milliliter. If a 6-gram bar of manganese is added to 35 milliliters in a graduated cylinder, to what level will it rise? So the key word's rise. So you know that the number can't be any lower than 35. Oh, but all the answer choices are above 35, so that works out. So you have a 10-gram bar. You need to figure out what the milliliters, or how much water displacement does a 10-gram bar of manganese is it responsible for. So you use the density to figure that out. You would divide by the density, because you know that if 7.3 grams is 1 centimeter cubed, then 10 grams is how many? So it'd be 10 divided by 7.31. So we can do, or 7.3, sorry. 10 divided by 7.3, and we get 1.37. So that'd be 1.37 milliliters. Now we can add 1.37 to 35, and that equals 36.4. So, I mean, if we round to the correct number of significant figures, which is 3, or in this case, since we're adding, it would just be 1 decimal place. So it would be 36.4 would be our answer. Okay, this one, iron makes up 0.008% by mass of the elements found in the normal normal healthy body. How many grams of iron would be in a person weighing 210? All right, so if iron makes up that much percent, that doesn't mean you multiply it by 0.008. That means you multiply it by 0.008 divided by 100, because it's a percent. That's a very, very small percentage. There's multiple ways you can do this. You can take the pounds, convert to kilograms, and then multiply by the percentage. Or you can multiply by the percentage first, then convert that new mass into kilograms. So whatever you want to do. And then you can end up converting that to grams because that's what the answer suggests. I think the answer is pretty small. I think it's 0.106 perhaps. But yeah. Okay, so which among the following represents a set of isotopes? Isotopes, same number of protons, different number of neutrons. So 1 and 2 are isotopes. They have 19 protons each and different number of neutrons. And that's it. So it's just 1 and 2. So B. All right, this one. You are given a compound with the formula M3N2, which M is a metal, N is nitrogen. You're told that the metal ion has 25 electrons. What is the metal? Nitrogen has a -3 charge, right? So there's 2 of them here. 2 of them means -6. Then that means the M's must be +6. In order for M's to be +6, what's the charge of each M? And I'll ask you guys. So what's the charge of each M? What do you think it would be? There's only 5 of you, so you can't really turn it on somebody else. So nitrogen is -3, right? There's 2 of them. Aha, I knew it. I caught everybody off guard. This nitrogen is -3. There's 2 of them. That's -6. That means the metal, M3, what would the charge of that be? What would the charge of each M be? Anybody? The charge of each M. So nitrogen. So in this question, you're asking for what is the identity of the metal if you know that the ion has 25 electrons. We know the formula is M3N2. So that means you have 2 times nitrogen's charge is -6. -3 times 2, that's -6. What is the charge then of each M? That's the first way to answer this question, first part to figure out. +2, good. So if each M is +2, that means for the ion to have 23 electrons and the charge is +2, its protons must be 2 higher than its electrons, meaning 27. So if we look in the periodic table, which element is number 27? Where's the periodic table? Oh no. Oh, maybe it's in the bottom. Yep. Well, it's on the bottom of the other ones too. So let's see. Yeah, so 27 is cobalt. If you remove 2 electrons from cobalt, its electron configuration becomes like number 25, like manganese. So that's right here. So that's cobalt. Okay, next. What is the mass of oxygen in 1 mole of that? So if that's the case, if you have that formula, then we can figure out the mass of the molar mass of it. And the molar mass would be aluminum's mass, which is 27 times 2, plus there are 3 carbons, so that's 36, plus there is now 9 oxygens. So 9 times 16, and that equals 234. So 234 is the molar mass, which you should all know how to figure out. Now, what is the mass of oxygen in 1 mole of it? So you basically just take the molar masses of the oxygens where there's 9 of them. So 9 times 16, which is the mass of the oxygens, you get 144. So that's going to be D. You didn't need to do the first part because it just asked about oxygen. Okay, next. Hypothetical element X has naturally occurring isotopes that give the average atomic mass of 24.2640. And the information below. Calculate the percent abundance of the isotope X25. Report to 1 sig fig. Now, if you know the abundances, or you don't know the abundances, you can figure that out. And if you know the atomic mass of each of the isotope and the average. So the equation that you can set up, where's my pen? All right. My PowerPoint out. I think I've done this on one of the homeworks before. Let's see. So what you can set up is you can set up, I'll put isotope X times its abundance. So we don't know about the abundance yet, but I'm going to put something in here. Or wait, hold on. And we'll do this, whatever. Plus isotope Y times 100 minus A. And this is going to be A. Or 1 minus A, that's better. Equals average atomic mass. So this is the kind of equation you would set up where you have A is a percentage and 1 minus A is the opposite percentage. So if you had an isotope X, which was 15 point whatever, times its percent abundance, plus the other isotope, which is, let's say, 14 point whatever, times 1 minus the previous abundance, because the abundances have to add up to 100%. That's why we do 1.0 minus A and then this A. And then we would end up with the average atomic mass on the right side of the equation, which then would give us the information to calculate A. It's kind of a pain in the ass to calculate if you don't have a calculator. So I suggest picking up one if you do not have one for the exam. Okay. Next. Oh, clicked the wrong thing. All right, so that's that. Which of the following choices is correct for the species described? So you have phosphorus, its atomic mass is 30, or its isotopic mass is 33, and its charge is -3. So if its charge is -3, phosphorus is located right here. If the charge is -3, that means it gains 3 electrons. 1, 2, 3. That makes sense. It goes to argon's electron configuration because that's happy. So now take a look at the question. Phosphorus is element number 15. So that means 15 protons have to be a thing. Since its charge is -3, then 18 electrons have to also be a thing. So 15 protons, 18 electrons. That's correct. So yeah. And also you can double, triple check with an isotopic mass of 33. You take the protons and the neutrons. If they equal 33, then you're good. And they do. Okay, next. A sample of methane has a mass of 40. How many molecules are in the sample? So you first find the moles by dividing by the molar mass of methane, which is 16, yes. And then you would take that number of moles, multiply it by Avogadro's number, and you're good. So it should be something really big, 10 to 23rd, whatever. Okay, next. Phosphoric acid can be prepared using this reaction. When the equation is balanced, the sum of the coefficients. So you have, on the left side, you have 3 calciums. Here, you'd have to put a 3. Then the PO4s are good. You need a 2 here. So 3 here. So right now it's 1, 1, 2, 3. Or 3, 2. 1, 1, 3, 2. And then H2, there's H3. And you have to put a 3 here. That makes sense. You put 1, 3, 3, 2. So 1 plus 3 is 4. Plus another 3 is 7. Plus 2 is 11. No, it's 9. Sorry. Yes, so 9. Okay, so chromium forms a series of oxides when combined with oxygen. In one compound, chromium is CrOx. And that many molecules have 1 gram. So what you would do is you can divide by the Avogadro's number. Now Avogadro's number and the molar mass specifically tells us grams per mole, right? So if you went back to that problem, you can kind of do grams per mole. you can convert this to 10 to the 21st into moles, and then you can take grams divided by moles, meaning grams per mole. You take the 1 gram, divide it by whatever number you get there, and that'd be your grams per mole. So that's an easy way to figure that out. All right, next, naming. So what I did with naming is I recently published a YouTube video on how to name different compounds, so definitely check that out and subscribe. The correct way to rename VN is, since N is just nitrogen, nitrate, nitride. What you would do is you would have vanadium, which would then be a +3 charge. Since it's a 1-to-1 ratio, you have vanadium, 3, nitride. So C is the answer. Number 16, which of the following is the highest percent of chlorine, or by mass of chlorine? It's whichever one has the most damn chlorines. So it's D. A molecule has the empirical formula of CH. One molecule contains 72 grams of carbon. What is the formula? Yeah, Adi, you have a question? Oh, wait, chlorine. My bad. Yes. Number 16, it says chlorines, not oxygens. I'm exhausted. Okay. So the answer would be A, because they all have the same number of chlorine, but the molar masses increase as you go down from A to D. This means the percent of chlorine decreases as you go down from A to D because the number of chlorines are staying the same and the mass is increasing. Therefore, A is your answer. So, Adi, great job in backing me up there. I appreciate it. Okay, so number 17. Molecule's empirical formula of CH, 1 mole contains 72 grams of carbon. So if we divide that by the molar mass of carbon, 72 divided by 12 is 6. This means that a mole of it has 6 carbons. If it has 6 carbons, and the ratio is a 1-to-1, C to H, then it's probably going to be benzene, C6H6. So that'd be the molecular formula. All right, choose the pair that has that's most likely to form an ionic bond. So we went over this kind of recently when it has to do with ionic strength and let's say the bigger charge numbers and the smaller the ion, then the stronger the charge. So out of all of these, we need to find one that has a large charge and it has both non-metal and metal. So K and Na, they're both metals. Nope. Silicon and carbon, not metal, non-metal. Selenium and oxygen, nope. Silicon or sulfur and nitrogen, nope. Zinc and chlorine, yes. That's a very good one to be. This is very easy. A compound of that many percents, what is the empirical formula? All right, so I think I will go over empirical formula just to refresh everyone's memories. Oh, wow, I am exhausted. Good thing we're almost done with this class. I can't take it. No, but you guys make it possible or bearable. Could be worse. All right. Okay, so a compound has 6.7%, 6.7, we'll just turn it into grams of hydrogen, 40 grams of carbon, 53.3 grams of oxygen. So the way we do empirical formula is we first take the number or the percentages given and convert them into grams. Done. Then we're going to figure out the molar mass of each one of these. Dividing by their molar mass. So 12.01 grams per mole. Oxygen is 16 grams per mole. And then we will calculate the answer. I will look at get my phone calculator real quick. 6.7 divided by 1.008. That would give us 6.65. That's going to be moles. Then we're going to do the same thing for the middle. We have 40 divided by 12.01. That's going to be 3.31 moles. Then we're going to do 53.3 divided by 16, 3.33 moles. All right, so now once we have the moles, we divide by the lowest number. So in this case, we're tied. 3.3 seems to be the lowest of the moles. We divide by that to simplify it. This means that there's 1 carbon, 1 oxygen. Divide this by 3.3. I'm assuming you get 2. So you have nothing wrong, nothing there. Yeah, so you have how many? 2. You have 2 there. 2 hydrogens. So that means our empirical formula is going to be CH2O, like that. Okay, cool. And if you had a molecular formula, they would give you the molar mass of it, and you'd multiply, or you would see how many times the empirical formula goes into the molecular formula. Then you multiply by that number. Okay, now part B. So, and let's see, the melting point of indium is 156.2 Celsius at 323 Fahrenheit. What is the physical state? So you want to see if it melted already or if it didn't melt already. So we convert Celsius to Fahrenheit using the equation that they provide. And just to skip the trouble, 156.2 Celsius to Fahrenheit is 313. So it would be below the melting point. This means it would still be solid. Next, determine the mass of that many grams of it, which, I mean, that's pretty much unit conversion. Determine the mass of potassium. So basically, you know that potassium bromide is KBr. So find the molar mass of KBr. See what percentage of potassium is in the molar mass. Multiply by that percentage. Multiply 35.5 by that percentage. That's one way to get to the answer. Next, this one, you have a reaction. Complete the equation by filling in the missing component and balancing the balance the equation with the smallest number of coefficients. So gaseous ammonia reacts with gaseous oxygen to form gaseous nitrogen monoxide and gaseous water. So they give you the answer, nitrogen monoxide, NO. And then you are going to balance it. Either put in two in front of the NO and 2 in front of the NH3. Maybe your fraction in front of the O2. But hopefully balancing should be pretty good by now. All right, now this one is a longer empirical formula. So who wants me to go over it? If not, it's okay. But if you do, I will go over it. No, but I mean, it's similar to the one we just did. All right, I'll explain conceptually what you do. So combustion of 2.175 grams of our unknown compound produced this much CO2 and this much water. In a separate experiment, a certain amount of the compound was found to contain that much nitrogen. From that sentence alone, you can figure out the percent nitrogen. Okay, I'm glad to hear that. Then you can use the CO2 to figure out the moles of carbon. Then you can figure out the moles of hydrogen using the H2O production. And then you can use the percent nitrogen and oxygen to figure out what's the missing amount of oxygen, or of hydrogen, sorry, to figure out what the missing amount of oxygen is. And then you can find all that information and then do our division by the lowest number and multiply or divide as necessary. Okay. All right, so I'm going to stop that one.